Welcome to a quick review of combination circuits or combo circuits. Combo circuits are circuits that are a combination of both series and parallel circuits. For example, R2 and R3 are in parallel, and they're also in series then with R1. And then R3 and R4 are in series, but their combination is in parallel with R2, and then when we combine them, then they're in series with R1. So, combo circuits have a little bit of both, some series parts and some parallel parts. When we're going to analyze these combination circuits, we usually the key is to start farthest from the source and then work back to the source, and then you can work back out to find individual quantities. For example, the source right here is this battery, and we have this resistor is the farthest away from this source, R3 is. So we look at R3 and we say, how is it connected to the company or the nearby other resistors here? We can see that it's in parallel side by side with R2. So the first step would be in analyzing this particular combination circuit would be to combine these two resistors in parallel, and then once I combine those in parallel, I would get one equivalent resistance over here, and we could see that that one equivalent resistance would be in series with R1. Once we've found that, we could find the total current flowing by adding the series elements then. And once we find the total current, we can find this voltage drop across R1, and then we can find this voltage drop across R2, and then that would be the same as this one and so forth. So you go from farthest away, you crunch things back inward to find the equivalent resistance, and then you take things back out to find individual quantities. So in this particular circuit down here, you have R3 and R4 are farthest away, and you can see that they're in series, so you could add those together, and then once you get that equivalent resistance, you can see that that's in parallel with R2, so you could find the equivalent parallel resistance here then, and then you'd have one equivalent resistance for all this, and we could see that that's in series with R1. And then once we find that equivalent resistance, we could find the total current flowing if we knew the total voltage that was given, and we go from there. Let's take a look at an example, the one that we've been talking about. Let's put some numbers in play here, and that we can talk about it more specifically. In our combination circuit up here, we can see that R1 is in series with a parallel combination of R2 and R3. So again, starting farthest from the source here, R3 is in parallel with R2. So our first step in solving this would be to find the equivalent resistance of these two parallel resistors here. Since both resistors are 4 ohms and we only have 2 resistors here, we can use our products over our sums equation here. And so 4 times 4 is 16 ohms squared divided by 8 ohms will give us 2 ohms. So these two in combination give us 2 ohms. Notice that whenever you have equal resistors in parallel, the parallel resistance of those is half of either of the resistors. If I had a third resistor in parallel here, so it's 4 ohms, 4 ohms, and 4 ohms, then it would be 1/3 of those. But anyway, that's a nice thing to know, that if you have equal resistors in parallel, the equivalent resistance is half of either of the resistors. So once we find that 2 ohms here with that parallel part, we visualize the circuit now as still our R1 here, but now this branch right here, this part of the circuit, this leg of the circuit, is now 2 ohms, the parallel combination of R2 and R3. And this is common language or notation for that, where you show 2 and then parallel lines 3, showing that this resistor is R2 in parallel with R3. And that's 2 ohms. So now we have a series circuit. So our next step would be to combine these two resistors in series, and doing that we would get a total resistance that the source senses of 6 ohms. All right, so once we get that 6 ohms total, we know that the current coming in and also going out is the total current, which happens to also be I1 in this case, going through this first resistor. So we can find that total current now because I is equal to V divided by R. So 24 divided by 6 ohms through Ohm's law is 4 amperes. So we have 4 amperes flowing into our circuit here. And since we have 4 amperes flowing, the next thing we could do is, going back up here either way, if I know there's 4 amps flowing through 4 ohms, I could find this voltage drop from here to here, V1, the voltage across this resistor. And so finding V1 here by taking V is equal to I times R, so 4 amps times 4 ohms is 16 volts dropped across V1 right here. So if I have 16 volts dropped from here to here, there are two ways that you can calculate the voltage drops here. We know that these voltages are going to be the same because they're in parallel. One way you could do it is using Kirchhoff's voltage law. I have 24 volts to start with. I've just lost 16, so I know that my voltage across from here to here to round out my loop here has to be 8 volts, because 24 minus 16 is 8 from here to here, because then there's no more voltage drop to get back here. So that's one way we could work now, is to say that using Kirchhoff's voltage law, that this voltage is 8 volts and this voltage is also 8 volts, since these are in parallel. The other way we could do it is coming back here. We know that 4 amps here flows through 2 ohms, and so 4 times 2 is 8 volts. So that's the other way you could have done it in this particular case. So either way, you have 8 volts across each of these resistors, and since we have 8 volts driving current through 4 ohms each, we get 2 amperes flowing in each of these branches. Another thing you could have realized is if we have 4 amps flowing in here coming into the node, then it has to split here and here. Since these are equal resistances, it would split equally here and here. So 4 amps would split into 2 amperes and 2 amperes. If you did that first, you could do 2 amperes times 4 ohms is 8 volts. So multiple ways you can go about finding these other values. But the process is always to start farthest away, break down the resistance into one equivalent resistance. And once you get that equivalent resistance, you can find the total current and then start chipping away at using Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law to solve for the rest of the circuit. So our example 2 here looks pretty ominous, lots of stuff to it, but we are going to use everything we know about series and parallel circuits here. That the voltage across parallel elements is the same. The sum of the currents at a node is 0. That's Kirchhoff's current law. The sum of the voltages around a loop equals 0. That's Kirchhoff's current law. The current is the same in series. Resistances add in series. Resistances divide in parallel. And if 2 resistors are equal and they're in parallel, the equivalent resistance is half of either of the values. So in this case, it would be 2 ohms. And in fact, that's where we're going to start, because when we have combination circuits, you always start farthest from the source. You break everything back down, and then you can build everything back up. So that's our strategy here, is to start farthest over here from our source and break all these resistances down and find an equivalent resistance, and then build everything back up. So starting over here, farthest away from the source, is R5. We can see that it's in parallel with R4, and since they're equivalent equal resistors here, the equivalent resistance here is 2 ohms. You could also use the products over sums equation to find that out for yourself too. So I visualize one resistor right here equal to 2 ohms with these combined. Then I can see that that 2 ohms is going to be in series with R3, which is 2 ohms, and resistors add in series. So 2 ohms plus 2 ohms is 4 ohms. So now I visualize all three of these combined into one resistor, which is 4 ohms. Well, that 4 ohms is in parallel with R2, which is also 4 ohms. So again, 4 ohms in parallel with 4 ohms is 2 ohms. And so now I visualize all of these resistors crunched down into one resistance of 2 ohms. So once I get that one resistance of 2 ohms, I can see that I have 2 ohms plus 2 ohms plus 2 ohms is an equivalent resistance of 6 ohms. Now that I've found the equivalent resistance of 6 ohms, I don't really have to visualize that as one single resistor because it's a simple series circuit here. 6 ohms, I can find the total current. I6 and I1 are both the total current here because whatever is coming in has to go out and vice versa. So I is equal to V, 24 volts, divided by R, which is 6 ohms. So 24 divided by 6 is 4 amperes. So I1 is 4 amperes and I6 is also 4 amperes. Now we start building things back up. We start moving back in the other direction. So we first of all break down and find one equivalent resistance. We find the total current then, and then build everything back up. So now that I know that this is 4 amps flowing through 2 ohms, I know that the voltage drop here is 4 times 2, which is 8 volts. Well, this is also equivalent of 2 ohms. So 4 amps flowing through this equivalent here of 2 ohms is 8 volts here. And likewise 4 amps flowing through 2 ohms is another 8 volts here. And that should make sense because 24 minus 8 is 16, minus 8 more is 8, minus 8 more is 0. Kirchhoff's voltage law says that the sum of the voltages will be 0. So things working out so far. Next, what I'm going to do, I know that this is 8 volts here, so I can find out what the current flowing through that equivalent 2 ohms here, well that's 4 amperes. I can find out what this current is going this way. Now I visualize, I start building a circuit back up. I visualize this 4 ohms, but now I visualize it in parallel with the 4 ohms that we had previously here with these three combined. So we have 4 ohms in parallel with all of this junk, which is 4 ohms. Well, if I have two equivalent resistances here and here, I know that this current has to split equally. So we have 4 amps breaking into 2 amps and 2 amps. And so now I know what I3 is, 2 amperes. Once I know that I3 is 2 amperes, I can find this voltage drop, V3. 2 amperes times 2 ohms is 4 volts. Well, we had 8 volts here. We just lost 4 volts, so the voltage across V4 here, across R4 is V4 is 4 volts. And since these are in parallel, V5 is also 4 volts. And so we can see that 4 volts divided by 4 ohms is 1 ampere. And that makes sense because we have 2 amperes coming in here, and it would split equally 1 ampere and 1 ampere. So this is a complex circuit, but you can see that if you kind of are systematic about it, you use all your series and parallel understanding here and Kirchhoff's current and voltage laws, you break the resistances down, then you build back out, then that's how you attack combination circuits. Scratch's parting thought. And good luck on your circuit toward continuous improvement.